All right, so now we're going to do example 4, and we have already done this example graphically in example 1b, but we're going to now use L'Hopital's rule. Scratch first. So the first thing that we have to verify is that we do have an indeterminate form, and in example 1b, we showed we have an indeterminate form of type 0 over 0. Okay. Now we need to say that we can take the derivative of the numerator and the derivative of the denominator, that those are both differentiable functions. So my numerator function is e to the 1 over x minus 1, and the denominator function is 1 over x. These guys are both differentiable. All right, let's take the derivative of g first, just because I see part of g showing up in f. To take the derivative of 1 over x, I'm going to first write it as x to the minus 1 power. G prime, using power rule, is minus 1 x to the minus 2 power. G prime is minus 1 over x squared. F prime, we're going to need chain rule. The derivative of e to that stuff is e to the stuff. Chain rule times the derivative of that stuff, the derivative of 1 over x we just did, is minus 1 over x squared. And minus the derivative of 0 is, or sorry, minus the derivative of 1 is just minus a 0. So we don't need to write that. Okay. The third thing that we need to claim is that the derivative of the denominator function is not equal to 0 for x values near wherever we're approaching, and in this case we're approaching positive infinity. So 3 g prime, which is minus 1 over x squared, is not equal to 0 for x values near positive infinity, approaching positive infinity. Now, note that the limit as x goes to positive infinity of minus 1 over x squared, that is minus 1 over huge. That limit is 0, but we're saying in L'Hopital's rule, we don't want the derivative of the denominator function to be equal to 0 for x values near where you're approaching. And that is the case here. Okay? So by 1, 2, and 3, we can use L'Hopital's rule. What do we have? The limit as x approaches positive infinity of e to the 1 over x minus 1 all over 1 over x is equal to the limit as x approaches infinity of f prime. You know, and how about multiply fractions straight across? Minus e to the 1 over x all over x squared. Or not. Doesn't really matter. I'll just leave it the way we had it. F prime over g prime. e to the 1 over x times a minus 1 over x squared all over the derivative of g, which is also a minus 1 over x squared. We have a secret times 1 here as long as x is not 0, and we're approaching positive infinity. I'm not interested in x being 0. So we've got e to the 1 over x, period. As x gets big and positive, 1 over x is on its way to 0. So we've got e to the 0, which is on its way to 1. Maybe I'll write it like this. As x approaches positive infinity, 1 over x is on its way to 0. Therefore, e to the 1 over x is on its way to e to the 0, which is 1. And that is the answer that we got in our graph. All right, now what I want to confirm on Desmos, to really understand the claim that we're making with this equality sign, I want to see that x values that are big and positive map to y values that are near 1, both on my blue curve and on this pink curve here. These are different functions, but they have the same limit. All right, so here's my blue curve, e to the 1 over x minus 1 all over 1 over x. Here's this pink or red curve that was the derivative of the numerator function divided by the derivative of the denominator function. And notice that as x gets big and positive on both of them, sorry, I zoomed out a little too much, on both of them, their y values get very close to 1. So they have the same limit.